is motion. Okay? And so, we're going to talk about a few things. Talk about speed, acceleration, what those mean, how to grasp them. We'll also talk about Newton's laws. Okay? Called Newton's laws of motion. From there, we will move into simple machines and mechanical advantage, and that'll be the end of what we need to cover for this section. So like we said, speed is defined as the distance something travels divided by the amount of time that it took it to travel that distance. That's average. That's what we call average speed. So when I ran this morning, I ran that mile. I wasn't running at a consistent pace. Started off a little too strong. I slowed down eventually. But my overall average speed during that time was 0.15 miles per minute. And say you take a trip in a car, you calculate your average speed. You may stop at a stoplight. You may go through faster speed limit zones and slower ones. But overall, you take the total distance divided by the time it took, and that's what speed is, and that's how we calculate speed. So, a couple examples. If a bird's traveling 100 kilometers and it takes 5 hours, it's speed. Okay, we follow the steps like we always do when we're using formulas. Speed is distance over time. What's the next step?
100 divided by 5.
Substitute our numbers, including units. And finally,
20.
do the actual math and
You was like 20 miles
with the
per
proper
hour?
units. So 20 kilometers
I
per
mean,
hour.
kilometers?
Yep.
It's like kilometers.
A rocket traveling 1,400 meters in 30 minutes. Again, distance divided by time, 46.7.
A minute?
Okay.
So wait, is the speed equal? Does that speed have to lie?
Speed is equal to distance divided by time. And constant speed is when something is traveling, guys, listen, is when an object is traveling at the same speed without it going up or down. Like a car in cruise control. Now velocity, I'm sure you've heard the word velocity, is something that's slightly different. The technical definition of velocity, okay, includes both the speed but also direction. Okay? So if you're asked for a velocity, usually, you're going to have to write a number with units and a distance as well. For example, if you say a train's velocity might be 130 kilometers per hour south. Okay? So it's traveling south. If the speed changes, its velocity changes, but also if its direction changes, its velocity changes. If that train makes a turn and starts heading east, then its velocity will change because now it'll be traveling 130 kilometers per hour east. So that's what this question is. If the direction changes, velocity changes. Now, if you've ever been in you see this lots of times in a big airport where they have those moving walkways to take you from one terminal to another. You ever get on those and walk the opposite way?
Yes.
Or when you walk in the same direction that it's taking you, what's it like?
It's like
You're walking very quickly. If you go up the escalator, if you walk with it, it seems like you're going very quickly. Or if you're one of those goofy people that try and walk down it,
I want
then it's a lot slower.
Oh, one time I walked up and down one, and I was like so much.
Yeah. So those are cases of combining velocities. So for example, if you have a man on a train traveling 200 kilometers per hour due west, and the person is also walking forward within the train, okay, at a speed of 5 kilometers per hour, what would his total velocity be? That's
205 kilometers per hour due west.
yes. He's traveling the same direction. He's walking as well as moving in the train. The total is 205 kilometers west.
How do you know
He's walking in the same direction. We'll get there in a second. So if the train's traveling due west, 200 kilometers, but now the man is walking towards the back of the train at 5 kilometers per hour, what is his total velocity, Michaela?
195 kilometers.
We need one more thing because this is a velocity.
I don't know.
Sarah? Due west.
Wait, what do you mean due west? I'm confused with the west.
His overall direction of travel, he's still, even though he's walking towards the back of the train, his overall movement is still going west. Because the train's going 200 kilometers per hour west, he's walking the opposite direction, only 5 kilometers per hour. Okay, just like if you were able to walk on that moving walkway, the exact same speed that it's going, and you're walking backwards, what's going to happen?
0.
Yeah, you're going to be 0. You're just going to be staying in one place. Okay, so then what is acceleration? What we've been talking about, speed and velocity, what's acceleration? Nicholas?
Like when you speed up.
Okay. Matthew?
The change in velocity over a period of time.
It's a change in velocity. We often use the word acceleration when we're talking about speeding up. Technically, you can have a negative acceleration, and that's still considered acceleration, but it's actually slowing down. So, we have a formula we use to calculate acceleration. Okay. And the formula is the change in velocity over time. So if a rocket goes from 0 to 20 kilometers per second in 10 seconds, what's its acceleration? Don't look at your paper if you can't help it. Michaela?
What's acceleration?
What is the rocket's acceleration in this example?
But you said the definition.
Yusuf?
2 kilometers per second.
2 kilometers per second per second. Or we often say per second squared.
Wait, how do we test that?
So, listen, acceleration is the change in speed divided by the time. In this case, the change in speed went from 0 to 20. So the change in speed was 20 kilometers per second. The time it took for that change to happen is 10 seconds. 20 divided by 10 is 2 units. Again, we do the same mathematical functions to units that we do to the numbers. So kilometers per second divided by seconds is kilometers per second per second.
Why is it per second per second?
Because kilometers per second. So it's changing its velocity 2 kilometers per second every second.
So it's like, you can put like a parentheses around the first 2
Kind of.
kilometers per
Or it's
second.
often written as kilometers per second squared.
I'm still kind of stupid.
Because for every second you're slowing down you're speeding up 2 kilometers per second.
So every second you're speeding up 2 kilometers.
Every second your speed is increasing
Oh.
2 kilometers per second. So if you start at 4 kilometers per second, a second later it'll be at 6 kilometers per second. All right, a person motorcycle goes from 7 kilometers per hour to 37 in 2 minutes. Try not to look at your paper. What's the acceleration? Victoria?
Wait, no, I thought that.
What are our steps?
Wait, that's not on that.
That's not on yours? Oh, it's not on mine either. Who has an answer though? Vedant?
5 kilometers per second.
No? Nicholas?
15 kilometers per hour per hour.
No, not quite, but close.
No, oh, wait. Okay. 15 kilometers per minute
Nope.
Dang it.
Sarah?
15 kilometers per hour.
Nope.
60.
Matthew?
15 kilometers per hour squared.
Nope. Ayla?
I'm thinking 15. The 15 kilometers per minute squared.
Nope. Sarah?
15 kilometers per hour. Kilometers per hour.
No.
50, I know it.
Lindsay?
Can I get a share?
No.
I know this one.
Jax?
1/4 kilometer per minute.
Nope. Oh my God.
I don't get that.
Nicholas?
Alright, 15 kilometers per hour per minute.
Yes.
Oh,
That's what I was
geez.
saying.
All right, let's look at it
How
though.
did you get that?
Let's look at it. So,
I get it.
acceleration
Oh.
is change in speed. So, what was the change in speed?
I don't know.
15.
It went from 7 kilometers per hour to 37. 30 kilometers per hour was the change in speed.
Divided by 2?
What was the time?
15.
2 minutes.
Oh.
Or 15 kilometers per hour per minute. every minute the speed was increasing 15 kilometers per
I
hour.
don't understand how you find.
You use combined the units, kilometers per hour, and you had to divide by the time, which was in minutes. So kilometers per hour per minute.
What was the answer?
15 kilometers per hour per minute.
Why just per hour per minute?
Because the speed is in kilometers per hour, the time was in minutes. All right, acceleration could also be negative. When an object decreases in speed, it's considered negative acceleration, or sometimes called deceleration.
Accelerate. Accelerate.
Did I say those words?
Yeah.
Yes, I might have
What?
been trying to explain this concept before we were ready. All right, now one of the things that we talked about is a graph. Now, I might skip the, well, let me go, I'm going to do this quickly. We're going to focus more on the next. There's two types of graphs to know about. This graph is showing what information?
The velocity.
Velocity
Accelerate.
versus time. So if you look at this graph, time is here in minutes, the velocity is here in meters per second. So this is a boat traveling. What is happening here in the first section?
Accelerate.
It's speeding up, accelerating. What's happening here?
It's staying on the same speed.
Constant speed,
Slow.
decelerating,
Constant.
constant speed. Okay. So in this type of graph, the slope represents acceleration. How steep that line is an indication of if it's how quickly it's accelerating. A plateau represents a constant speed. And the steeper the slope, the greater the acceleration.
Mr. Ross, I'm confused.
About what?
Everything.
Well, I can't help you if you just say you're confused about everything. Do you have a question about something?
Yeah, well, it's on the front page. I'm confused. I'm so,
The formula for speed?
yeah, kind of.
So it's the distance something travels, just divided by the time it took to travel that distance.
That's it.
That's all. So if you leave here after school and your house is 6 miles away, and it takes you 25 minutes to get there on the bus, the average speed of your bus would be 6 miles divided by 25 minutes. And the units would be miles per minute, because the distance was measured in miles, the time was measured in minutes.
Okay.
Okay, another graph. So what was this boat's speed between minutes 2 and 10? Is this answered for you? All right, don't look at it, just look at the
I'm not on
board.
that.
All right, what was its speed between minutes 2 and 10? I should say velocity. What was its velocity, Matthew?
Wait. I forgot it.
Oh, 8.
Sarah?
Isn't it 8 minutes?
8 meters per second. That's meters per, yeah, it was 8 meters per second.
I don't understand how you're doing it.
So between minutes 2 and 10, I want to know what was its speed or velocity. So the problem, what I should not have on here, I should have consistent labeling. Really, this should say speed. And these could say speed. But anyway, it's 8 meters per second because that's where it was between minutes 2 and 10. Was its speed constant during that time, Adon?
Yes.
Yes, it was. How do we know? Because the line is flat. It stayed at 8 meters per second.
Wait.
Yes.
What?
Yeah.
Oh no, I got confused on number 1. I thought it was like from 1 to 2.
Okay,
Not 2 to
so
10.
what was the boat's acceleration between minutes 0 and 8? Between minutes 0 and 8. Ayla?
1 meter per second per minute.
Yes. So, again, what do we need to know? The acceleration, okay, is the change in velocity over time. Between minutes 0 and 8, what was the change in velocity? 8 meters per second. What was the time? 8 minutes. So 8 meters per second divided by 8 minutes is 1 meter per second per minute. All right. When was this boat acceleration the greatest? Matthew?
1 to 2, no, 0 to 2 minutes?
Yeah, between 0 and 2 is when this line was the steepest. Dude?
Do speed and velocity and time graphs, do they always start at 0, 0?
Not always, but usually. Now, we have a different type of graph.
Wow.
What are these, how are these graphs different? Sir?
They don't have like the time and stuff.
Well, they do have, oh, you mean, no numbers? Yeah, they could have numbers though, but it's giving you some different information. Yusuf?
Grants different things.
Yeah. It still has time on the x-axis, but what's on the y-axis? Distance. So these sort of graphs mean different things. So, as time goes on, the distance that this object has traveled, okay, it gets a farther and farther distance away. What's happening here at B then?
Staying the same distance.
It stopped. It's staying the same distance. If I start off at this door, and you were to measure my distance that I've traveled from this door every second or so, okay, I start, my distance would be going up, I'm getting farther away. Then I stop, now time's still going on, so my graph would be continuing, but my distance away from the door stays the same. When I start walking again, my graph starts increasing.
Is
It
that
stops.
when you go down? Is that when you go back?
How can it go down?
When you go back into reverse.
Yes. If I reverse, then the graph would go down because my distance is decreasing.
So that person went up, stop, and then went back.
So let me ask you this question. Did I already ask you this?
I don't know.
If I walk halfway across the room.
Victoria cannot get it. She asked.
Oh yeah, when would I reach there?
Never. Wait, I forgot what this one is.
If I walk halfway across this room and continue walking half the distance to the end of the room every second, when will I arrive at the end of the room?
Never.
Never. Never.
I don't know why.
Because you always are getting a smaller and smaller distance, but you never actually get to zero.
You're only doing half the distance.
That bugs me.
There we go. Actually, can I try this?
What?
10 by 10.
Yeah, you're gonna walk forever? No. All right. So the slope of this line on these sort of graphs represents the speed of an object. If the line is at a constant slope, the object's moving at a constant speed. A plateau in this case means stopped. And if the slope is steeper, it's moving faster. It's traveling a greater distance in a shorter time. Its speed is faster. What's this graph showing? Kayla? Hold on. Yep.
So, what if the person was at a consistent rate, like on the first one, like consistent, like
Speed.
yeah,
Then
speed?
the-
What if
The line would just continue
what if like
diagonal. Nope. What's this show? That's, yeah, acceleration, because this line is getting steeper over time. This object's speeding up.
I don't think
This room?
no that the last day of like our class
Yeah.
we're taking
I
final
know.
because you're a mean teacher.
Really? What do you think you're gonna have field days?
Yeah.
No, that's all.
No, I think we're gonna do Monday.
No.
I think you should cancel the final for sure.
Your fun days, the rest of your summer vacation. All
I
right.
like this. I like this. No problem.
All right. This graph. What does this show?
Acceleration.
Deceleration.
Wait,
Why D?
Because the line starts off steep and getting less and less steep.
Oh.
Fix this. So
All right.
It's a rainbow. It's.
We draw a graph of a biker accelerating from a red light, reaching a constant speed. That's what it would look like.
Acceleration.
Yes.
Where it is. Stop.
We just kept going. All right. Good.
Does it have to subject to kind of and then straight up?
What, huh?
Mr. Dross,
Wait a second. Let me explain what you need to do.
this is homework. You're not giving us homework.
You have homework, right?
So much homework.
You have both have homework. Remember that?
Mr. Dross.
Mr. Duras. Mr. Duras.
like studying her body.
So you're just giving us one homework? Mr.
Overreact.
You're overreacting. What is digital blasphemy?
I don't know. Must be where that little clip art is. There you go.
You could have given me a paper for my eye.
We need a.
That would be unfortunate. Then you look like me.
I have a story about that. My sister actually gave her friend a paper cut on the eye. She almost wrapped her. I don't want this. I know, right? It's pie!
Alright, here's what I would like you to do. Let's answer some
I don't want that.
questiones.
Take this back, I don't want it. Thank you.
Yeah, that's a real Spanish word.
That's not.
It's actually
Questiones.
Preguntas.
I'm going to give you the blood guy.
Wait, no,
All right.
the wrong one.
Alright, let's start on 313.
313.
Yeah, 313.
313.
The problems.
We have 2 313s.
Answer those 4 questions. Go, quickly, go, ready now.
In the motor.
This is.
Alright, solve these problems. Yeah, you may use a calculator, you may use and should use a calculator on your final exam.
Mr. Ross, you made me put my calculator. I lost it.
I left it by
Wait, is this basically like a quarterly or this is for the
No, it's a whole year. Whole year.
Mr. Ross, how am I supposed to know at the beginning of the year?
You're supposed to get copy of the notes and study.
But I don't have any of the notes.
We're going to review them a little bit.
just said you had a copy of the notes. Wait, can we round?
Well, yeah, you can round to a 10th place.
Oh.
Mr. Ross. Remember?
No,
No, I left it.
bring your own.
No, I
Too
was.
bad by hand, it's good for you.
No, I was being nice, and I left it back. He answered crazy. And he lost it. I lost it? Yeah. No. Here we go.
You done yet?
I'm done with the first one.
Let's go.
Hey, wait.
All of them, all 4.
Oh, there's not
We're going to talk about Newton's laws, people.
Isn't that like I know these. No, that's one.
The one gravity pull.
Alright, just go. What around this?
I know there's one that what an object in motion
Hey, let's go. Let's go.
I know that one too.
Mr. Ross.
I got it.
Got the second one too.
I'm on the
I already did the third one, so.
Hey, Mr. Ross, I understand this.
Wow.
I don't get number 4 now.
Don't really get the fire extinguisher.
I need something to drink, Mr. Ross. Wait. Is this
Go get a drink. Hey. Mr. Duras, these are the ones with the kilometers per second.
Come on. That is. Alright, let's go over them.
Oh no, I've only done 2.
Number 1.
Dang, let it
Motors travels 400 kilometers during a 7-hour period. What was his average speed? Kayla,
57.1 kilometers per hour.
57.1 kilometers per hour. Got it?
Yeah.
A rocket is launched to space goes 240,000 kilometers per hour. No, during the first 6 hours. What was its average speed? Brian?
40,000 kilometers per hour.
40,000 kilometers per hour, yes. A bullet leaves a rifle. 5 seconds later, it's 3,000 meters away. What is its speed, Victoria?
600 meters per second.
Yeah, 600 meters per second. Last, an electron in a vacuum travels the length 2 meters in 0.002 seconds. What was its speed? Kimberly? 1,000 meters per second. Yeah.
You lied to me.
Got 'em? Easy, right?
Yeah.
These are homework.
No. We just went over that. All right, now look at the graphs. Let's do some of these together.
It is staying constant.
Object
I
A
mean,
and object B. What is happening to them? Raise your hand, please. Vidon.
object A, it's decelerating because it's, well, I mean, it's not like.
Wait, object what?
Oh, wait, it's accelerating an object. Okay.
No, neither one are accelerating. Nicholas?
They are both coasting to speed they currently are.
They're both moving a constant. This is distance versus time.
I thought the constant was when I was.
Distance versus time. So a graph that's straight means every period of time you're covering the same distance, which means you're at a constant speed. Which one has a greater speed?
B.
A or B, Ayla? B does. All right, another distance versus time graph on the right. What happened to the object between 0 and 12? Nicholas?
Okay, it was traveling at the same speed and then it leveled out.
Which
Then it
means,
It stopped.
yeah, so it's traveling at constant speed and then it stops. Because the line gets flat and its distance stops changing.
Just a slam on the straight arc.
What about this object on the right? What's happening to that object? Victoria?
It's accelerating, but then it starts to decelerate.
It's actually decelerating the entire time.
Yeah.
You know what you should do? It's something
Because the line is curving, getting flatter and flatter.
Mr. S, what's B for number 2?
Okay?
Yeah, but it goes like,
It's going this way. It's getting less and less steep.
it's accelerating at first, isn't it?
No, because it starts off very steep, and each second it's getting a little less steep. So it's
By the
decelerating.
beginning, but why doesn't it accelerate? Because it's so steep.
It doesn't matter how steep it is. It's what's happening to the line. Is it straightening out or is it getting steeper? And the whole time it's flattening out.
Oh.
What's happening to the object in number 4, Matthew?
It's accelerating.
It's accelerating.
Okay, let me just leave with time.
All right.
Are we done now?
No, we are not done now. We still have to talk about the laws of motion. So, Newton's laws of motion are 3 important laws that govern how things move in the universe on a large scale. And first, we need a definition of force. A force is a lift, a push, or a pull exerted on an object. That's what a force is. And we talked about 2 special types of forces in Newton's laws. Friction, which is what? You not? Yes, it's a force that resists motion. When 2 objects are in contact, moving across one another, there's always some amount of friction slowing down that movement, resisting that movement. And then another special type of force, gravity. What is gravity?
Oh, the force on Earth.
Okay, go ahead. Question about friction.
Friction, what about things where like the surface is slippery or slide something on the
Yeah, so ice, is there friction between your
Yes.
skates and ice?
Yes.
But it is
Lower.
much less than the friction between your skates and a rubber mat.
It's just like water. There's less gravity underwater than there.
Well, not less gravity.
But no, it's less buoyancy.
Yes, buoyancy supports your weight.
Because you get
Matthew?
just like air and oxygen. How they
No. So, air also resists motion. That's more considered air resistance. And gravity is an attractive force between 2 objects. When we think of gravity, we're talking mainly about the force between what object?
What goes up?
Earth and all the other objects.
Because Earth is the biggest thing.
But it's not only that the Earth has a gravitational pull on us, all objects in the universe have a gravitational pull on each other. So when you jump up and you touch the ground again, why do you touch the ground? Because gravity, but you are also pulling up on the Earth. You have gravity that's an attractive force between you and the Earth. So why don't you jump and then the Earth comes up to meet your feet?
Because the Earth's bigger.
Because of the giant mass of the Earth far outweighs your mass, therefore the force is
What if
much
we all
greater.
jumped at once?
Wait,
Still doesn't matter.
Jupiter and you put it on there and you made it like jump, then the Earth.
Yeah. All right.
But that's physics.
So let's talk about one of Newton's laws, maybe. The law of inertia.
I don't know if that sounds.
Newton's law of inertia says an object that's at rest will stay at rest.
And the body and
An object in motion will stay in motion. So, for example, Matthew's pencil here. Leave it. It's at rest, correct? And it's going to stay at rest. Unless acted upon by another force. And then it moves. Alright. Now, it also says that an object in motion will stay in motion. If I take a
Unless you crash.
Baseball.
Throw it to me. Throw it to me.
No, Mr. Gross, you should throw it to me.
I have no rolly objects at the moment.
I play baseball, so I
Alright, here I have a rolly
I
object.
play softball.
So if I take this glue stick and I roll it, is the glue stick in motion?
Yes.
Is it going to stay in motion?
No, it's another option.
Until it goes gravity.
No, watch, wait. So is the motion stay in motion? So did it just break Newton's first law of motion?
No, it didn't.
Why not?
Because there's an exception.
The
An object
outside-
in motion tends to stay in motion unless there's a friction coefficient.
Unless acted upon by an outside force. What outside force stops us? Friction.
And gravel.
Friction.
And gravel.
Friction. If we were to take this glue stick to some fictitious, non-existing, friction-free surface, it would roll forever. Like nothing.